Welcome to this presentation of common plating wastewater issues. My name is Robin Deal. I am a wastewater specialist working for Hubbard-Hall. I started my path in wastewater treatment nearly 10 years ago as a licensed physical chemical wastewater operator in North Carolina. I worked for a large hand tool manufacturer running 4 wastewater systems. When the facility I worked at was closed, I made the decision to join Hubbard-Hall rather than to relocate out of state. Since then, I have helped numerous manufacturers solve challenging and complex wastewater issues across the country. Today, we will be focusing only on wastewater generated from electroplating lines. Here are some fun facts about the history of plating. Well over 200 years old, this metal finishing process has become a staple in manufacturing. Precious metals like gold and silver were the first metals used in plating. John Wright invented cyanide plating with the discovery of solubility of gold and silver into potassium cyanide in the mid-1800s. Some of the first mass-produced plating products included silverware and pen nibs manufactured by Elkington and Mason. Russia is the home to the largest gold electroplated dome cathedral in the world. First built in the 1800s, the Cathedral of Christ the Savior was destroyed in 1931 by Stalin. Rebuilt in 2000, it boasts 5 gold electroplated domes with an Orthodox cross. While the history of electroplating is very rich and interesting, the environmental impact of the wastewater generated from the process cannot be overlooked. In 1972, the Clean Water Act came into being and gave structure for regulating the discharges of pollutants into the waters of the United States. Metal finishing guidelines can be found in 40 CFR Part 433 in the Federal Code of Regulations. There are 2 types of discharge permits. The first is an NPDES permit, which is given to direct dischargers. The second is a pre-treat permit, which is given to manufacturers who discharge to a city or municipality. Both are set into place to ensure that the receiving waters are not compromised by the discharge waters. The chart here shows the EPA's guide for both best available technology practices and best practical technology practices in regards to metal discharges. What challenges do electroplating shops face in today's world? Hexavalent chrome destruction, while seemingly simple, is often a challenge at facilities who work with it. Cyanide destruction can be dangerous if not completed correctly. Chelation is in every electroplating wastewater stream. Finally, removing those metals is hard for some systems. A pioneer in chrome plating, George Sargent earned his doctorate in 1912 by studying chromium disposition. United Chromium Incorporated was formed in 1927 with the merger of Chromium Corporation of America and General Chromium Corporation. During World War II, hard chrome plating was put on hold. In the 1950s, its popularity took off again. The French government created a Center of Information for Hard Chrome, which supplied the world with a comprehensive textbook on the subject in 1952. Hexavalent chrome is a known human carcinogen. To be successfully removed from wastewater, it must be reduced to its trivalent state. The most common way to do this is to isolate any stream containing hexavalent chrome. Lower the pH to 2.5 or below using an acid. Introduce a reducing agent such as sodium metabisulfite or ferrous sulfate while watching for a positive 250 ORP reading. Maintain the 2.5 pH and the positive 250 ORP reading for up to 15 minutes to ensure that the entire solution is reduced to the trivalent state. Once this is accomplished, the stream can then be bled back into the main wastewater stream for metals removal if the system is a flow-through. If the system is a batch treatment, this step should be done before proceeding to the coagulation stage of metal removal. Alkaline chlorination for cyanide destruction is the most common practice used in the metal finishing industry. It can be dangerous if not completed properly. The cyanide stream is isolated for the destruction process. Alkaline chlorination is a two-step process. The first step is the formation of cyanogen chloride at a high pH, 10.5 or higher. Sodium hypochlorite is introduced to see a positive 550 or higher ORP reading. While maintaining the high pH and ORP reading of the solution is allowed to mix for up to 1 hour. This will allow the cyanogen chloride to form cyanate. The second step is to lower the pH to 8.5 or 9. This converts the cyanate to ammonia and carbonate. Once the second stage is complete, solids will form. Allow them to settle out before returning the wastewater to the main stream for metal removal. Chelation is a necessary evil in the electroplating process. It can be found in the cleaners as well as the plating baths. Some forms are relatively easy to treat, while others can tie up an entire system for days. There are several ways to break chelation bonds, making metal removal easier for the wastewater system. The oldest method is to lower the pH to 2, add calcium, raise the pH back up to 11, and flock the solution out. This method can use large amounts of chemistry and produce excessive amounts of sludge for disposal. The addition of metal precipitants such as DTC or sulfides can prevent the wide pH swings. Metal precipitants can be dosed by ORP readings or by establishing a known dosage amount during bench testing. If basing dosing on ORP readings, watch for a 50-point or more drop in ORP to know that enough has been used. Set dosing typically falls at less than half a milliliter per gallon to break chelation bonds. Metal precipitants should always be added at the higher pH. Overdosing these can cause problems as well, so be careful to keep an eye on your dosing. If you hold an NPDES permit, there are environmental concerns with some metal precipitants. Research the products you are using carefully. Consult with the experts in the field if you are in doubt. Most metal finishing shops use hydroxide precipitation to remove metals from waste streams. Metals are naturally insoluble at a specific pH if there is no chelation present. The formation of hydroxide salts occurs when a hydroxide, such as sodium hydroxide, is introduced to the metal-bearing waste streams. As the pH rises, the hydroxide forms bonds with the metal, thus making it insoluble. In most cases, a coagulant will be needed to help with the removal of mildly chelated metals. Coagulants can be iron, aluminum, calcium, rare earth, or a blend of these depending on the system's needs. Added at lower pHs, when hydroxide is introduced and the pH is raised, coagulants give the metals such as chrome and nickel an extra bond to stabilize them in the insoluble form. You can see this with the formation of pin flock in wastewater systems. Depending on the metals needed to be removed, the pH can be lower or higher. Nickel comes out best at a pH of 10.5, while chrome is removed at a pH of 9. The object is to find the pH range where all of the metals would form hydroxide salts and fall out equally. If the waste stream has more of one metal than the other, the pH would then be adjusted more toward the pH of the prominent metal. Once pin flock is formed, a flocculant will need to be added to clump the pin flock together to form larger flock that will settle rapidly in a quiet tank or clarifier. Most often, the flocculant will have an anionic or a negative charge to attract the positive charge of the metals. Flocculants can come in emulsion, dry, or ready-to-use forms. If it is an emulsion or dry form, it is typically made down to a 0.1 to 0.2% dilution in a day tank or blending unit prior to being added to the system. A typical metal finishing wastewater system can be as small as 1 tank for batch treatment. In batch treatment processes, everything is done in that one tank. Some batch treatment systems hold multiple tanks so that one tank can be filling with untreated water while a second tank is being treated and a third tank is settling for solids removal. Wastewater systems can also be designed to allow the wastewater to continually flow through the system while it is being treated at each stage. The key is the system should fit the manufacturer's needs. A new system should take into consideration the current wastewater generation rates along with projected 10-year growth patterns. Undersizing a system can cause short-circuiting, solids overflow, metal removal issues, along with numerous other problems. Oversizing a system can cause overfeeding of chemistry, stagnant water that produces odors, and underfilled filter presses, among other things. When a manufacturer has been in operation for a number of years, it is a good idea to review the wastewater system to ensure that it still meets the needs of the present-day manufacturing processes. Wastewater treatment will never be a moneymaker for manufacturers. There are ways to make sure it doesn't break the bank, as they say. Routine checkups on the system and with the operator's help can see where problems may be in the treatment processes. Addressing issues as they arise rather than patching them can mitigate some costs. Completing regular bench testing to make sure that the coagulants and flocculants are still the best for the process is always a good idea. Asking questions from chemical suppliers and educating everyone who touches the wastewater system on things that can go wrong and how to fix them as needed are steps to any successful wastewater treatment program. Wastewater treatment isn't black magic that is worked in the dark. It is chemistry in its least complicated form. Thank you for taking the time to listen in. I hope you gained at least one piece of new knowledge today. I look forward to more presentations such as this one, and I hope you will join in on those as well.